Hey guys, I wanted to give sort of an introductory video on electric potential. And hopefully by the end of this video, we'll see that electric potential, or voltage, as you might have heard it termed, is really just a ratio between two physics quantities that you've already learned about. So first, let's consider the change in electrical potential energy as an electric charge moves through an electric field. We find that as the electrical potential energy increases, we'll be doing work on the charge in the opposite of the direction that we define as positive. Likewise, if the electric potential energy were decreasing, work would be done in the same direction that we define as positive. So we describe that as the following mathematical sentence. Delta U sub E is equal to negative W sub E. The change in electrical potential energy is equal to the opposite of the work done on the electrical charge. That is to say that the change in electrical potential energy opposes the direction of the work performed on the charge. Now that we have a mathematical understanding of electrical potential energy, we could define a new concept, electrical potential or voltage. Let me write this in maroon. Electrical potential. And you might have heard this referred to as voltage. And we see that voltage actually arises from the unit that we use to measure electrical potential. So what is electrical potential? Well, electrical potential is defined as electrical potential energy per charge. So that is V. So V is electrical potential, is equal to U sub E divided by Q. That is, it's the ratio between the electrical potential energy and the charge. So a change in the voltage, which we call the electrical potential difference, which is delta V, is actually the change in electrical potential energy divided by the charge. So the unit for electrical potential and electrical potential difference, because electrical potential difference is just the difference between two measurements of electrical potential. The unit for that is, let me write this, unit is, well, the unit for energy of any type is a joule, and the unit for charge is a coulomb. So the unit is a joule per coulomb, which we commonly refer to as a volt. So a joule per coulomb is equal to a volt. That's where the term voltage comes from. Let me write this, volt. And I want to remind you that potential energy and electrical potential are scalars. So it doesn't matter the direction of an arbitrary point from the charge because the electrical potential at all points the same distance from the charge is the same. And that's kind of intuitive. They're not vector quantities, they're scalar quantities. So you could think of them as the circles of possible points originating around an electric charge have the same potential. And these were called equipotential surfaces. Equipotential surfaces. So I'm going to embarrass myself with my poor drawing now, but let's say that we have a point charge, which we could call P, and then let's say that we have a circle, a locus of points around it. The electrical potential at any point in this circle, this locus of points that falls around P, has the same value. So all these points to which I'm drawing the arrows right now have the same electrical potential in relation to the point P. Thus, we refer to the ring of the points, or the circle, as an equipotential surface, because all points along the surface have the same electrical potential in relation to the point P. Thanks for joining me, and I will see you in the next one.